The idea of artificial intelligence, of machines that can think and learn like humans, has captivated our imaginations for centuries. Long before the advent of computers, stories of artificial beings, from ancient myths to science fiction novels, explored the potential and perils of creating artificial minds. These early visions, though often rooted in fantasy, planted the seeds for the field of artificial intelligence as we know it today.
The formal pursuit of AI began in the mid-20th century, fueled by breakthroughs in computer science and a growing understanding of the human brain. Pioneers like Alan Turing, John McCarthy, and Marvin Minsky dared to ask a fundamental question: can machines think? This question, seemingly simple yet profoundly complex, ignited a scientific revolution that continues to this day.
The early years of AI were marked by a sense of optimism and ambition. Researchers believed that building intelligent machines was just a matter of time, a challenge that could be overcome with enough computing power and ingenuity. This era saw the development of the first AI programs, capable of playing checkers, solving mathematical theorems, and even carrying on simple conversations. These early successes, though limited by the technology of the time, fueled the belief that human-level AI was within reach.
In his seminal 1950 paper, Computing Machinery and Intelligence, Alan Turing proposed a test that would come to define the field of artificial intelligence. This groundbreaking idea was not just a theoretical exercise but a practical challenge to the scientific community. Known as the Turing test, it provided a practical, albeit controversial, benchmark for measuring machine intelligence. The test was revolutionary because it shifted the focus from the internal workings of the machine to its external behavior.
The test is deceptively simple. A human evaluator engages in a text-based conversation with an unseen entity, either a human or a machine. The simplicity of the test belies its profound implications for understanding intelligence. If the evaluator cannot reliably distinguish between the two, the machine is said to have passed the Turing test, demonstrating a level of intelligence indistinguishable from that of a human. This criterion has sparked numerous debates and experiments over the decades.
The Turing test, despite its limitations, sparked decades of debate and research into the nature of intelligence and consciousness. It challenged scientists to think about what it means to be intelligent and whether machines could ever truly replicate human thought. It shifted the focus from defining intelligence in abstract terms to developing machines that could exhibit intelligent behavior, regardless of whether they possess true understanding or consciousness. This shift was crucial in advancing the field of AI. This pragmatic approach paved the way for the development of practical AI applications, even in the absence of a complete understanding of the human mind. From healthcare to business, AI began to find its place in various sectors, transforming the way we live and work.
While the Turing test has served as an important benchmark, it is not without its critics. Some believe that the test is too focused on human-like behavior, which may not be the only or even the best measure of intelligence. Some argue that it focuses too narrowly on mimicking human behavior, potentially overlooking other forms of intelligence that may not conform to human-like thought processes. This has led to the exploration of alternative benchmarks and tests. Others point out that passing the Turing test does not necessarily equate to true intelligence or consciousness, as a machine could potentially fool a human evaluator through clever programming without possessing genuine understanding. This raises questions about the nature of intelligence itself. Nonetheless, the Turing test remains a powerful concept, a testament to the enduring human fascination with creating machines that can rival our own intellectual capabilities. It continues to inspire and challenge researchers, pushing the boundaries of what machines can achieve.
The 1950s and 1960s marked a period of rapid progress and excitement in the field of AI, often referred to as the golden years. During this time, the possibilities seemed endless, and the enthusiasm among researchers was palpable. Fueled by substantial government funding and the emergence of powerful new computers, researchers made significant strides in developing AI systems capable of solving complex problems that had once been considered the exclusive domain of human intelligence. These advancements were seen as groundbreaking and opened up new avenues for exploration.
Programs like Cite, developed by James Slagel, could solve symbolic integration problems at the level of college freshmen, showcasing the potential of AI to handle tasks that required a certain level of cognitive ability. While Sherdlu, created by Terry Winograd, could understand natural language instructions to manipulate objects in a virtual world. This was a significant leap forward in natural language processing and demonstrated the potential for AI to interact with humans in more intuitive ways. These early successes led to a wave of optimism, with some experts predicting that human-level AI was just around the corner. The media was abuzz with headlines proclaiming the imminent arrival of intelligent machines, and the public imagination was captured by the possibilities.
However, the limitations of the prevailing approaches to AI soon became apparent. Despite the initial successes, researchers began to encounter significant challenges that tempered their early enthusiasm. Early AI systems, while impressive in their ability to solve specific problems, struggled to generalize their knowledge to new situations. They were often rigid and lacked the flexibility needed to adapt to new and unforeseen circumstances. They lacked the common sense and adaptability that humans take for granted, making them brittle and prone to errors when faced with unexpected inputs or changes in their environment. This brittleness highlighted the gap between human and machine intelligence.
The limitations of early AI, coupled with unrealistic expectations and the withdrawal of government funding, led to a period of disillusionment and reduced investment in the field, often referred to as the AI winter. This period was marked by a significant slowdown in progress and a re-evaluation of the goals and methods of AI research. While research continued in specialized areas, the dream of creating general-purpose artificial intelligence seemed distant and elusive. Researchers focused on narrower, more achievable goals, hoping to build on the foundations laid during the earlier period of optimism. However, the seeds of future progress had been sown, and the lessons learned during this period would shape the future direction of AI research. The experiences and insights gained would eventually lead to new breakthroughs and a renewed sense of possibility in the field of artificial intelligence.
Section 4. Neural networks and the rise of machine learning. As the limitations of early AI systems became apparent, a new paradigm began to emerge: machine learning. Instead of explicitly programming computers with rules for every possible scenario, machine learning algorithms could learn from data, identifying patterns and making predictions without being explicitly told what to look for. This shift marked a significant departure from traditional AI approaches, opening up new possibilities for innovation and problem solving.
This approach held the promise of creating more flexible and adaptable AI systems, capable of handling the complexities of the real world. Among the most promising machine learning approaches were artificial neural networks, inspired by the structure and function of the human brain. These networks aim to mimic the way human neurons process information, allowing machines to learn and adapt in ways that were previously unimaginable.
Neural networks consist of interconnected nodes or neurons organized in layers. Each connection between neurons has a weight associated with it, representing the strength of the connection. By adjusting these weights in response to training data, neural networks can learn to recognize patterns, make predictions, and even generate creative outputs. This process, known as training, involves feeding the network vast amounts of data and iteratively refining the weights to improve accuracy and performance.
However, early neural networks faced limitations of their own. Training these networks required large amounts of data and computational power, both of which were scarce at the time. As a result, neural networks remained a niche area of research, overshadowed by other machine learning techniques that were more computationally feasible with the limited resources available. Researchers often struggled with the slow processing speeds and limited memory capacities of early computers, which hindered the progress of neural network development.
Nevertheless, the potential of neural networks to revolutionize AI was evident to those who continued to explore their capabilities. These pioneers believed that with advancements in technology and increased computational power, neural networks could eventually overcome their early limitations and unlock new levels of AI performance. Their persistence laid the groundwork for the breakthroughs that would come in the following decades as neural networks began to demonstrate their true potential in a variety of applications. Section 5. Deep Learning: Unlocking the Power of Data. The 21st century witnessed a resurgence of interest in neural networks, fueled by the exponential growth of data and computing power. This new era, dubbed the Deep Learning Revolution, saw the development of vastly more complex and powerful neural networks, capable of learning from massive datasets and achieving unprecedented accuracy in tasks such as image recognition, natural language processing, and game playing.
Deep learning algorithms, characterized by their multiple layers of interconnected neurons, proved particularly adept at extracting complex patterns from raw data. This ability stemmed from their hierarchical structure, allowing them to learn representations of data at increasing levels of abstraction.
For example, in image recognition, lower layers of a deep neural network might learn to detect edges and textures, while higher layers might learn to recognize objects and faces. This breakthrough in deep learning had a profound impact on numerous fields, from medicine and finance to transportation and entertainment.
Self-driving cars, once the stuff of science fiction, became a reality, powered by deep learning algorithms that could perceive and navigate the world around them. Virtual assistants like Siri and Alexa could understand and respond to human speech with remarkable accuracy.
Deep learning was rapidly transforming the technological landscape, opening up new possibilities and challenges in equal measure.